All right, folks, we're going to talk about chapter 4.3. You'll notice that I skipped 4.2. In a normal lecture, I would cover 4.2, but I'm going to let that slide. Not that it's not important. It is very important, the mean value theorem. So I'm going to go right to what derivatives tell us about the shapes of functions. So I'm concentrating on this whole thing of how the first and second derivative test can point out things about the shape of a function. We've already talked about maxes and mins, and now we're going to talk about concavity and points of inflection. So for this example, I'm choosing this function. Nice, friendly polynomial. It's a cubic, okay? So what I would do first, just so we kind of know what we're dealing with, this is for your viewing pleasure. I'm putting it into my graphing menu and taking a look what the graph looks like. Now I can see by looking at this that there is certainly one local max and one local min. Okay. Now we're looking at this globally. We're not looking at this on a closed interval. In other words, we're looking at this from negative infinity to positive infinity. So since we've already done some of this, I'm going to go ahead and take the first derivative here and find out where these maxes and mins are. So I see that y prime is equal to 3x squared minus 6x. And I'm going to set that equal to 0. So I'm going to solve this. So I have x times 3x minus 6. Set that equal to 0. I'm going to get two solutions. I'm going to get one at x equals 0. And I'm going to get one at x equals 2. Now I am going to find the y coordinates of these because I'm emphasizing this to you that when you find these critical points on this curve, which are going to be maxes and mins in this case, that you need to supply the y coordinate. Now, certainly I could just plug this in by hand. Certainly the x equals 0, I don't really have to use my calculator because I can see that that's y equals 6. And when I plug in the x equals 2, and I'm going to use my calculator for this because it's certainly easier. It's at y equals 2. Now I do know ahead of time that this first one, I can just see it, I can see it from the picture on the graph, that this is a local max. And that this one over here is a local min. Okay. Let me show you this. Now, again, I'm choosing a really friendly example here, guys, but that's what we need to demonstrate the concepts here. This applies no matter what the function is. Okay. Now, this means that I have intervals of increasing and decreasing. Okay. So I will write these down for you. So I have negative infinity to 0. It's increasing. It's 0 to 2. It's decreasing. And then it's 2 to positive infinity. It's increasing again. Now, by definition, even though we already know this by looking at the shape of this, if we have a function that is going from increasing to decreasing, that means that point must be a maximum. And if we have a function that's going from decreasing to increasing, we know that that point must be a minimum. So this just confirms what we already know. But you will be asked in the book and maybe on an exam to give intervals of increasing and decreasing using proper interval notation. Notice these are open intervals. And make sure that you understand interval notation. If you don't, look it up on YouTube and make sure that you have done some reading up on it. Okay, now I'm going to go to my second derivative of this function. That's going to yield me the points of point or points of inflection. So I've got y double prime is equal to 6x minus 6. And I'm going to set that equal to 0, just like I did the first one, when I get x equals 1. So I'm going to use my calculator and find that the point is y equals 4. That is a point of inflection. Okay, let me show you this. And then I'll show you the calculator, which shows you that this point of inflection is where the curve changes its shape. Okay, I'll show you this in a second after you've taken a look at this. All right, this is second derivative test. All right, so notice here where the flashing cursor thing is on the curve, that's the place where the curve changes its shape. It's going from concave down to concave up. I'm looking at this from, of course, from left to right. So it's going from concave down to concave up. Concave down means it doesn't hold water. Concave up means that it does hold water. That is the shape of the function. Okay, this is what derivatives tell us about the shape of a function. One of the last things that they ask you about in the book and in WebAssign is to give the intervals of concavity. So here we go. One more time, interval notation. So from negative infinity to 1, it's concave down. And from 1 to positive infinity, it's concave up. So this simple example has everything in it. Now, agree, many other functions are going to be a lot more complicated than this. But this is the essence of what we're doing with the first and the second derivative test, including making sure that you understand how to use interval notation. Now, of course, in class, I would spend more time in a lecture on this, but seeing nobody shows up for Zoom sessions, many of you are going to be left to your own devices to try to figure some of this out. So this takes us up to 4.3, okay? Most of the other stuff in this chapter are all related to first or second derivatives and what they tell us, including to the applied section that we're going to get to on optimization. Okay, that's more applied stuff. All right, so hopefully you guys are reading these, watching these videos, and actually keeping up with us. We're more than halfway through this course. All right, I'm going to end this. Here we go. Goodbye.